Picture the most powerful force you can imagine. Now multiply that by infinity. That's barely scratching the surface of what black holes represent in our cosmos. These aren't merely celestial objects floating through space. They're tears in the very fabric of reality itself, regions where the laws of physics bend so dramatically that time, space, and matter behave in ways that seem almost impossible. What makes black holes so captivating isn't just their raw power. It's the mind-bending implications they have for everything we think we understand about the universe. They challenge our notions of time, mock our understanding of gravity, and potentially hold secrets about the nature of reality that we're only beginning to glimpse. I'm your host, and this is Late Space. Over the next journey together, we're going to explore these cosmic enigmas from every angle. We'll examine how they're born from the violent deaths of massive stars, understand why nothing can escape their gravitational embrace, and discover the strange phenomena that occur in their vicinity. We'll dive into cutting-edge theories about what might happen inside them, explore whether anything could ever truly escape, and investigate the bizarre connection between black holes and the fundamental nature of our universe. By the time we're done, I hope you'll see black holes not as terrifying cosmic monsters, but as windows into the deepest mysteries of existence. If this exploration captures your imagination, I'd appreciate your support through a like and subscription. The spectrum of black holes. Before we plunge into the physics, let's establish the sheer variety of these objects scattered throughout our universe. The range is absolutely staggering, spanning many orders of magnitude in both mass and size. At the smaller end of the spectrum, we find what astronomers call stellar mass black holes. The tiniest one ever detected weighs in at approximately 3.8 times the mass of our Sun. To put this in perspective, imagine cramming nearly 4 suns worth of material into a region so compact that it essentially becomes a point in space. The forces required to accomplish this are beyond staggering. We're talking about densities that make neutron stars look practically fluffy by comparison. The event horizon of such a stellar mass black hole would have a radius of only about 11 kilometers. That's smaller than most cities. Yet within that tiny sphere of space, the gravitational field is so intense that it represents a fundamental boundary in the universe. Cross that line, and the geometry of space-time itself forbids your return. But stellar black holes are practically lightweight compared to their larger cousins. At the opposite extreme, we encounter supermassive black holes, gravitational behemoths that have existed since nearly the dawn of time itself. These titans can possess masses equivalent to billions of our suns. Their physical scale is equally impressive. The event horizon, the boundary beyond which nothing escapes, can stretch so wide that you could fit our entire solar system inside it comfortably. Some of these monsters have diameters measured in astronomical units, the distance from Earth to the Sun being just one such unit. To really grasp the scale difference, consider this. If a stellar mass black hole were the size of a marble, a supermassive black hole could be larger than the Earth itself. And we're not talking about different physical objects. We're talking about the same fundamental phenomenon scaled across an almost incomprehensible range of sizes. Between these extremes lie intermediate mass black holes, weighing thousands of solar masses. These are somewhat mysterious objects. We've found strong evidence for their existence, but they're harder to detect than either stellar mass or supermassive black holes. They seem to exist in the centers of some globular clusters and dwarf galaxies, but their formation mechanism remains debated. Then there are the supermassive black holes at galactic centers that tip the scales at hundreds of thousands to billions of times our Sun's mass. Nearly every large galaxy appears to harbour one of these monsters at its core. Our own Milky Way galaxy contains Sagittarius A, a supermassive black hole with a mass of about 4 million solar masses. There's even speculation about primordial black holes, hypothetical black holes that could have formed in the extremely early universe, fractions of a second after the Big Bang, when density fluctuations might have been intense enough to create black holes without needing a star to collapse. These could theoretically have any mass, from microscopic to massive. If they exist, they might even account for some or all of the mysterious dark matter that appears to dominate the universe's mass. Each category of black hole tells us something different about the universe. Stellar mass black holes teach us about stellar evolution and the deaths of massive stars. Intermediate mass black holes might reveal how supermassive black holes form and grow. Supermassive black holes give us insights into galaxy formation and evolution, as their growth appears intimately connected to the galaxies they inhabit. And primordial black holes, if they exist, would open windows into the physics of the very early universe, conditions we can barely begin to replicate in our laboratories. The birth of a black hole. Understanding how black holes form requires us to understand stellar life cycles, particularly for the universe's heavyweight stars. This journey from birth to black hole is one of the most dramatic stories the cosmos has to tell. When a massive star ignites in the depths of space, it begins an existence defined by balance. Two fundamental forces engage in an eternal tug-of-war that determines the star's fate. Gravity constantly pulls every particle of the star inward, trying to compress all that mass down to the smallest possible volume. This isn't a gentle pull, it's an overwhelming force trying to collapse trillions upon trillions of tons of matter into an infinitesimal point. Working against this crushing force is the star's internal furnace, and what a furnace it is. Deep within the stellar core, the temperature and pressure become so extreme that hydrogen nuclei, which normally repel each other due to their positive electric charges, are forced together with such violence that they fuse into helium. This nuclear fusion process is absolutely critical to understanding stellar physics. Let's pause here and really understand what's happening during fusion. Hydrogen nuclei are just single protons. Two protons naturally repel each other with electromagnetic force, because they're both positively charged. Under normal circumstances, this repulsion keeps them apart. But in the core of a star, temperatures reach 10 to 15 million degrees Celsius, and pressures are millions of times greater than atmospheric pressure at Earth's surface. At these conditions, protons are moving so fast and colliding so violently that they can overcome their electromagnetic repulsion. When they get close enough, another force takes over, the strong nuclear force, which is much more powerful than electromagnetism, but only operates at extremely short ranges. This force binds protons and neutrons together into atomic nuclei. When hydrogen atoms merge to create helium, something remarkable happens. The resulting helium nucleus actually has slightly less mass than the 4 hydrogen nuclei that created it. Where did that missing mass go? Einstein's famous equation, E=mc2, provides the answer. That tiny amount of missing mass gets converted into an enormous amount of energy. This is where the numbers become truly staggering. The conversion factor is c2, the speed of light squared, approximately 90,000 meters squared per second squared. Even an infinitesimal amount of mass, when multiplied by this astronomical number, yields tremendous energy. This energy radiates outward from the core as heat, light, and pressure, pushing back against gravity's inward crush. Photons generated in the core begin a long journey outward, colliding with particles, being absorbed and re-emitted countless times. A single photon can take hundreds of thousands of years to random walk its way from the stellar core to the surface despite travelling at light speed. For millions or billions of years, depending on the star's mass, this delicate equilibrium persists. The star remains stable, burning brightly in the cosmic darkness. More massive stars burn faster and hotter, exhausting their fuel in mere millions of years. Less massive stars, like our Sun, can persist for 10 billion years or more. The most massive stars, the ones destined to become black holes, might last only a few million years before their violent end. But nothing lasts forever. Eventually, the hydrogen fuel begins to run low. The core's temperature drops slightly as fusion slows. With less radiation pressure pushing outward, gravity gains the upper hand, compressing the core further. For stars massive enough to meet the criteria for black hole formation, this doesn't spell immediate doom. Instead, something remarkable happens. The stellar core, now filled with helium, contracts under gravity until it reaches even higher temperatures, around 100 million degrees Celsius. At these extreme conditions, helium itself begins to fuse, creating heavier elements like carbon and oxygen. This process continues in stages, each more dramatic than the last. As each fuel source depletes, the core contracts further, temperatures rise higher, and fusion of heavier elements becomes possible. The star develops a layered structure like a cosmic onion. Each shell represents a different fusion process occurring at different temperatures and pressures. The innermost core fuses the heaviest elements available. Surrounding it, a shell fuses the next lightest element. Further out, another shell fuses something lighter still. A massive star approaching the end of its life might have half a dozen or more concentric shells, each burning different fuels simultaneously. The star creates oxygen and neon, burning through these fuels in thousands of years, then silicon, exhausted in just days or weeks. The pace accelerates dramatically as the star works its way up the periodic table. Elements that took millions of years to exhaust get replaced by fuels that last mere days. Finally, the core begins fusing silicon into iron. This is where everything changes. This is where the star's fate becomes sealed. Iron represents a critical turning point in stellar evolution, and understanding why requires a brief detour into nuclear physics. When you fuse light elements into heavier ones, you're essentially packing nucleons, protons and neutrons more tightly together. For elements lighter than iron, this tighter packing actually requires less energy to maintain than the looser packing of the original lighter elements. The extra energy gets released as the fusion energy we've discussed. But iron is special. Iron-56, the most common isotope of iron, has the most tightly bound nucleus of any element. It sits at the very bottom of the nuclear binding energy curve. Fusing iron into anything heavier requires adding energy rather than releasing it. Similarly, splitting iron into lighter elements also requires energy input rather than releasing it. This means iron. Fusion provides no outward pressure to counteract gravity. The iron accumulates in the core, growing larger and more massive, but contributing nothing to the star's structural stability. It's dead weight, literally. The moment arrives suddenly and catastrophically. With no energy pushing outward, gravity wins decisively. The stellar core collapses in what can only be described as a cosmic implosion. The scale of this collapse defies easy comprehension. Material that was previously spread across thousands of kilometers crashes inward at speeds approaching 70,000 kilometers per second, nearly a quarter of light speed. The entire iron core, containing more mass than our Sun, can collapse from the size of Earth down to the size of a city in less than a single second. As the core collapses, several things happen almost simultaneously. The density skyrockets. Electrons get squeezed into protons, converting them into neutrons and releasing neutrinos in the process. Neutrinos are nearly massless particles that barely interact with ordinary matter. Trillions of them pass through your body every second from the Sun, and you never notice. But during a core collapse, so many neutrinos get created so quickly that even though each one barely interacts with matter, their collective energy becomes significant. The collapse continues until the material reaches nuclear density, the density of atomic nuclei themselves. At this point, the compressed matter suddenly becomes incredibly resistant to further compression. It's as if the collapsing core has hit a wall made of the strongest material imaginable. The infalling material slams into this suddenly resistant core with tremendous force. The violence of this collision creates one of the universe's most spectacular events, a core collapse supernova. When the collapsing material rebounds from the core, it generates a shock wave that propagates outward through the star's layers. This shock wave, initially carrying about 1051 ergs of energy, 10 billion ergs, blasts through the star's outer envelope. Within hours, the shockwave reaches the star's surface and erupts into space, blasting the star's outer layers across interstellar space in an explosion so bright it can temporarily outshine an entire galaxy of hundreds of billions of stars. For a few weeks, this single exploding star can emit more visible light than all the other stars in its galaxy combined. If a supernova occurred as close as 10 light-years from Earth, it would appear as bright as the sun in our sky, despite being 630,000 times more distant. In this cosmic cauldron, in the intense heat and neutron flux of the explosion, elements heavier than iron are forged. Gold, platinum, uranium, and all the other heavy elements that make up our technology and our world get created in these brief moments of nuclear alchemy. Every gold atom in your jewellery, every uranium atom in nuclear reactors, every heavy element on Earth was created billions of years ago in the death throes of massive stars. But what remains after this titanic explosion depends critically on the original star's mass, or more specifically, on the mass of the core that collapses. If the core's mass falls below approximately 3 solar masses, the neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed into the same space, manages to halt the collapse. The remnant becomes a neutron star. These objects represent one of the densest forms of matter in the universe, second only to black holes themselves. A neutron star might measure only 20 to 25 kilometers in diameter, about the size of a small city, yet contain more mass than our entire sun. The density defies imagination. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth, equivalent to a mountain compressed into a volume you could hold in your hand. The surface gravity is about 200 billion times Earth's surface gravity. Drop something from 1 meter above a neutron star's surface, and it would impact at millions of kilometers per hour within a fraction of a second. However, if the core exceeds that critical threshold of roughly 3 solar masses, physics takes us somewhere even more extreme. The crush of gravity becomes so overwhelming that nothing can stop the collapse. Not even the incredibly strong degeneracy pressure that keeps neutrons from occupying the same space can withstand the gravitational force. The core collapses past the neutron star stage, past any known configuration of matter. Our current understanding of physics cannot tell us exactly what happens next. The equations of general relativity predict that the collapse continues until all the mass reaches a single point of infinite density, a singularity. A black hole has been born. The transition from collapsing star to black hole happens in the tiniest fraction of a second, yet its consequences echo through space-time. The event, horizon forms, that invisible boundary beyond which escape becomes impossible. From the outside universe, the black hole appears suddenly, a dark wound in the fabric of space-time where a star once shone. The event horizon and space-time curvature. When you see an image of a black hole, that dark sphere dominating the center isn't actually the black hole itself. That darkness represents something called the event horizon, and understanding what it really is requires us to think about gravity in a completely different way than Newton taught us. For centuries after Isaac Newton published his Principia Mathematica in 1687, scientists understood gravity as a force, similar to magnetism or the pull of a stretched spring. Massive objects exerted a gravitational force on other objects, pulling them together across empty space through action at a distance. This model worked brilliantly for predicting planetary motions, calculating artillery trajectories, and explaining why apples fall from trees. Newton's law of universal gravitation stated that every massive object attracts every other massive object, with a force proportional to their masses and inversely proportional to the square of the distance between them. Simple, elegant, and remarkably accurate for most practical purposes. Then Albert Einstein came along in 1915 with his general theory of relativity, and everything changed. The revolution he sparked was so profound that we're still grappling with its implications more than a century later. Einstein proposed something that seemed almost mystical at first. he suggested that gravity isn't actually a force in the traditional sense. Instead, mass and energy warp the fabric of space-time itself, and objects move along the curves in this warped geometry. Imagine space-time as a stretched rubber sheet. This analogy has limitations, but it's useful for visualization. Place a bowling ball on that sheet, and it creates a depression, a dip in the fabric. Now roll a marble nearby. The marble curves toward the bowling ball, not because the bowling ball is reaching out and pulling on it with some mysterious force, but because the marble is simply following the straightest possible path across the curved surface of the sheet. The marble is following what's called a geodesic, the shortest path between 2 points in curved space. This is how gravity actually works according to Einstein. The Sun creates a deep well in space-time, and Earth orbits around it not because it's being pulled by a mysterious force action at a distance, but because it's following the straightest possible path through the curved space-time around the Sun. It's constantly falling into the Sun's gravity well, but also moving sideways fast enough that it keeps missing, creating an orbit. This reconceptualization of gravity had immediate and profound consequences. It predicted phenomena that Newton's theory couldn't explain. For instance, Mercury's orbit precesses. The point of closest approach to the Sun slowly rotates over time. Newton's theory couldn't account for the observed rate of this precession. Einstein's theory predicted it precisely. Even more dramatically, Einstein's theory predicted that light itself should be deflected by massive objects, since light follows geodesics through curved space-time just like matter does. In 1919, during a solar eclipse, astronomers measured the positions of stars that appeared near the Sun's edge in the sky. The star's light had passed close to the Sun on its way to Earth. The measurements showed that the stars appeared slightly displaced from their true positions, exactly as Einstein had predicted. Light from the stars had been bent by the Sun's gravitational field, or more accurately by the curvature of space-time around the Sun. This observation made Einstein world-famous overnight, and fundamentally validated general relativity. Shortly after Einstein published his theory, a physicist named Karl Schwarzschild began working through the mathematical implications while serving in the German army during World War I. Despite the chaos of war, Schwarzschild found an exact solution to Einstein's field equations, describing the space-time geometry around a perfectly spherical non-rotating mass. What he discovered was startling. He asked a profound question. Could there exist objects so massive, creating such extreme space-time curvature, that even light couldn't escape? The mathematics gave a clear answer. Yes. Schwarzschild calculated that for any given mass, there exists a critical radius, now called the Schwarzschild radius. If you could compress that mass down below this radius, the curvature of space-time would become so severe that anything crossing this boundary, even massless particles like photons of light, would find escape impossible. For Earth, the Schwarzschild radius is about 9 millimeters. To turn Earth into a black hole, you'd need to compress all its mass down to a sphere smaller than a marble. For the Sun, the Schwarzschild radius is about 3 kilometers. The actual Sun has a radius of about 700,000 kilometers, so we're nowhere close to black hole territory. But for objects that have already collapsed, neutron stars approaching or exceeding 3 solar masses, reaching the Schwarzschild radius becomes possible. This boundary became known as the event horizon, and it represents one of the most important concepts in all of physics. The term event horizon is beautifully descriptive. It's the horizon beyond which events cannot be seen, a boundary in space-time beyond which information cannot reach an outside observer. The event horizon isn't a physical surface. There's no wall there, no barrier you could touch or measure. There's no change in the fabric of space-time that you could detect locally as you cross it. It's simply a mathematical boundary that marks the point of no return. Cross it, and the geometry of space-time itself guarantees you can never leave. Not because there's a force preventing you, but because all paths through space-time, even those where you're travelling at light speed, lead inexorably inward toward the centre. To understand this properly, we need to recognize something profound about space-time. Here's where things get truly strange. Space-time isn't just space plus time as separate things. They're fundamentally intertwined, two aspects of a single four-dimensional fabric. Einstein showed us that what we think of as 3 dimensions of space and 1 dimension of time are actually 4 dimensions of space-time, and they can mix in ways that depend on your motion and the gravitational field you're in. When mass warps space, it necessarily warps time as well. The two are inseparable. The stronger the gravitational field, or more accurately, the more curved the space-time, the slower time flows relative to regions of weaker gravity. This isn't just theory. We've measured it with atomic clocks. Atomic clocks at different altitudes on Earth, where they experience slightly different gravitational fields, tick at measurably different rates. The difference is tiny, nanoseconds per day, but it's real and measurable. GPS satellites must account for relativistic time dilation, or they'd quickly become useless. The satellites orbit at about 20,000 kilometers altitude, where Earth's gravity is weaker, and time flows slightly faster than at Earth's surface, about 45 microseconds per day faster. Simultaneously, the satellites are moving at about 14,000 kilometers per hour, which causes time dilation in the opposite direction due to special relativity, about 7 microseconds per day slower. The net effect is that clocks on GPS satellites run about 38 microseconds per day faster than clocks on Earth's surface. This might not sound like much, but GPS determines position by timing signals from multiple satellites. Light travels 30 centimeters in 1 nanosecond. If we didn't correct for relativistic effects, GPS would accumulate errors of about 10 kilometers per day. Your navigation system would be useless within hours. Near a black hole, this time dilation becomes extreme. The massive curvature of space-time doesn't just bend the paths of objects and light, it stretches time itself. This creates one of the most counterintuitive aspects of black holes. Imagine you're watching a spacecraft falling toward a black hole's event horizon from a safe distance. From your perspective, far from the black hole where space-time is relatively flat, you would observe something bizarre. As the spacecraft approaches the boundary, it appears to slow down. It moves more and more slowly relative to your clock, and the clock aboard the spacecraft ticks at an ever-decreasing rate compared to yours. Radio signals from the spacecraft become increasingly redshifted, stretched to longer and longer wavelengths as time dilation increases. At the event horizon itself, from your perspective, time for the spacecraft appears to stop completely. The spacecraft would appear frozen, suspended just outside the boundary in a single moment stretched toward eternity. You would never actually see it cross the event horizon. But there's more. As the spacecraft approaches the horizon, its image would dim and fade. The light it emits becomes increasingly redshifted, eventually shifting beyond visible light into infrared, then microwaves, then radio waves, growing fainter and fainter. Long before the spacecraft technically reaches the horizon from your perspective, it would fade from view completely, becoming invisible against the darkness of the black hole. Yet, and this is crucial, from the spacecraft's perspective, nothing special happens at the event horizon. Time flows normally for the crew, their clocks tick at 1 second per second, as always. They wouldn't notice anything unusual at the exact moment they crossed this cosmic point of no return. They'd simply continue falling, experiencing time normally, watching the universe outside appear to speed up dramatically as they fall. From their perspective, they might see the entire future history of the universe play out in moments. Then the tidal forces would intensify, stretching and compressing them in a process gruesomely nicknamed spaghettification, until they're torn apart at the atomic level and eventually impact whatever lies at the center, probably a singularity. This is one of the profound mysteries of black holes. Two observers, one falling in, one watching from outside, can experience radically different realities, both equally valid within the framework of relativity. The falling observer crosses the event horizon and experiences a finite amount of time before destruction. The distant observer never sees the event horizon crossed, watching instead an eternally frozen image slowly fading to invisibility. Both perspectives are correct. Both are real. This isn't a trick or illusion. It's a fundamental feature of how space-time works when curved this severely. Beyond the event horizon, something even stranger occurs. The extreme curvature of space-time becomes so severe that space and time essentially exchange roles in a sense. In our normal universe, you're free to move through space in any direction. Forward, backward, left, right, up, down. But you're forced to move forward through time. You have no choice about whether or not you'll experience the next second. It's inevitable. Inside the event horizon, this relationship changes. All paths through space lead inexorably toward the singularity at the center, just as all paths through time lead inexorably toward the future in our universe. You can't stop moving toward the singularity any more than you can stop moving toward the future. The singularity isn't somewhere in space that you're falling toward. It's somewhere in time, an event in your future that you cannot avoid. Meanwhile, different regions of space become accessible in strange ways. Some solutions to Einstein's equations suggest that rotating or charged black holes might have interiors containing paths to other universes or different regions of space-time. Wormholes, which we'll explore later. As far as acceleration is concerned, there's an elegant parallel to consider. Einstein's equivalence principle states that acceleration and gravity are locally indistinguishable. An observer in a closed elevator being accelerated upward at 9.8 meters per second, squared cannot tell whether they're accelerating or sitting still on Earth's surface. Near a black hole's event horizon, this principle remains valid locally. An observer falling through the event horizon wouldn't feel any sudden change or barrier. Locally, space-time appears smooth, but globally the causal structure has changed fundamentally. Escape has become impossible not because of a force or barrier, but because of the geometry of space-time itself, discovering the invisible. For decades after Einstein's theory predicted them, black holes remained purely theoretical constructs, mathematical curiosities that existed only on paper and in the imaginations of physicists. Many scientists weren't sure whether they could actually exist in nature, or whether they represented an idealized solution to Einstein's equations that the messy, complicated real universe would never quite achieve. Even Einstein himself had doubts. In 1939, he published a paper arguing that black holes couldn't form in nature because matter couldn't be compressed to the extreme densities required. He believed that some unknown physical process would halt the collapse before the event horizon could form. History would prove him wrong on this point, one of the few times Einstein's intuition failed him in matters of physics. The skepticism was understandable. Black holes seemed almost impossible, an object so dense that light itself couldn't escape, a region where the known laws of physics broke down. It sounded more like science fiction than science fact. But the mathematics was sound, and a few physicists continued to take the possibility seriously. In the 1930s and 40s, researchers like J. Robert Oppenheimer and his student Hartland Snyder worked out the details of stellar collapse, showing mathematically that sufficiently massive stars could indeed collapse past the point of no return, forming what we now call black holes. Still, without observational evidence, black holes remained speculative. You can't see them directly, that's the whole point. So how do you find something that's invisible, that emits no light, that's essentially a hole in space itself? The answer came with new technology that opened our eyes to invisible parts of the electromagnetic spectrum. The first real evidence emerged in 1964, thanks to X-ray astronomy, a field that had barely existed before then. Throughout most of history, humans could only observe the universe in visible light, the narrow band of electromagnetic radiation our eyes happened to detect. Radio waves discovered in the late 1800s opened a new window. Radio astronomy began in earnest in the 1930s and revealed a universe buzzing with radio emission from objects that looked ordinary or even invisible in optical light. but X-rays remained inaccessible. Earth's atmosphere, fortunately for us living on the surface, absorbs X-rays quite effectively. This protects us from harmful radiation from space, but it also meant that to do X-ray astronomy, we had to get instruments above the atmosphere. The space age made this possible. In 1962, a rocket-borne X-ray detector discovered the first cosmic X-ray source beyond the solar system, an object in the constellation Scorpius that was named Cygnus X-1. This opened a new field of astronomy. By 1964, scientists had recently developed satellites capable of detecting X-rays from space. These early X-ray telescopes were crude by today's standards, essentially Geiger counters pointed at the sky, but they worked. When they turned their new X-ray telescopes toward the heavens, systematically surveying the sky, astronomers began finding X-ray sources scattered across the cosmos. One source in particular caught their attention. In the constellation Cygnus, there was a powerful source of X-ray radiation, designated Cygnus X-1. The first curious thing about it was its variability. The X-ray emission flickered and varied on timescales of milliseconds to seconds. This rapid variability immediately told astronomers something important about the size of the source. Here's why. Imagine a source of light that's 1 light second across, about 300,000 kilometers, similar to the distance from Earth to the Moon. If something caused the entire source to suddenly brighten, we wouldn't see the change happen instantly. Light from the far side of the source would take an extra second to reach us compared to light from the near side. Any variation would be smeared out over at least 1 second from our perspective. The fact that Cygnus X-1 varied on timescales of milliseconds meant the X-ray emitting region had to be no larger than a few hundred kilometers across. Yet this tiny region was emitting as much X-ray energy as thousands of ordinary stars. Whatever Cygnus X-1 was, it was tiny and extraordinarily energetic. The second curious thing about it was that, oddly, they couldn't see any corresponding visible light source where the X-rays originated. This was unexpected and puzzling. Most astronomical X-ray sources are extremely hot, and hot objects generally emit visible light as well as X-rays. In fact, they usually emit far more visible light than X-rays. But Cygnus X-1 appeared to be emitting X-rays with no visible counterpart. This wasn't quite right, as it turned out. There was a visible star in that region, a blue supergiant star catalogued as HDE 2266868. But this star alone couldn't account for the X-ray emission. Its surface temperature was far too low to produce such intense X-rays. As observational techniques improved through the 1970s, astronomers made a crucial discovery about the system. Cygnus X-1 wasn't alone. It existed in a binary system gravitationally bound to that visible blue supergiant star, orbiting around each other every 5.6 days. This was the key that would unlock the mystery. You see, when two objects orbit each other, they provide a natural laboratory for measuring mass. By carefully watching the visible star and measuring how it moved, how quickly it orbited, how far it moved, astronomers could use Newton's laws of motion, which still worked perfectly well for describing orbits, even if Einstein gave us a deeper understanding of why they work, to calculate the mass of the invisible companion. The measurements took years to refine. The visible star was wobbling back and forth as it orbited the unseen companion. By measuring the star's spectrum carefully, astronomers could detect the Doppler shift in the star's light, the same effect that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it recedes. When the star moved toward us, its light shifted slightly toward the blue end of the spectrum. When it moved away, its light shifted toward the red end. By tracking these shifts over time, astronomers could measure the star's orbital velocity. Combined with the orbital period, this gave them the size of the orbit, and from the size and period, using Kepler's laws of planetary motion, which apply equally well to binary stars, they could calculate the mass of the system. The mathematics revealed something startling. The visible blue supergiant had a mass of approximately 20 to 40 solar masses, a heavyweight star by any measure. But the unseen companion, the X-ray source, had a mass of approximately 15 to 20 solar masses. This presented a problem, a big problem. This object was too massive to be a neutron star. Neutron stars, discovered as pulsars just a few years earlier in 1967, were known to be incredibly dense as atomic nuclei themselves. But there was a theoretical limit to how massive they could be. If you tried to pack too much mass into a neutron star, even the degeneracy pressure of neutrons, a quantum mechanical effect that normally prevents neutrons from occupying the same space, would be overwhelmed by gravity. The star would collapse further. Calculations suggested this limit was around 2 to 3 solar masses. Some uncertainty remained in the exact value because the properties of matter at nuclear densities weren't fully understood. But all reasonable estimates agreed. Neutron stars couldn't exceed about 3 solar masses. Cygnus X-1's invisible companion was 15 to 20 solar masses, 5 to 10 times heavier than the maximum mass for a neutron star. There was only one explanation consistent with the observations and with known physics. Cygnus X-1 was almost certainly a black hole, the first ever identified with any confidence. But how could they detect X-rays from something that emits nothing? The answer lies not in the black hole itself, but in the material falling into it. The system's configuration became clear. The visible blue supergiant star was being slowly devoured by its compact companion. Material from the outer layers of the supergiant loosely bound to the star was being pulled toward the black hole by its intense gravity. This material didn't fall straight in. It had angular momentum, so it spiraled inward, forming an accretion disk around the black hole. Within this disk, incredible forces were at work. Material orbiting closer to the black hole moved faster than material further out, as Kepler's laws demanded. This created shearing forces and friction between adjacent rings of orbiting material. Particles collided violently with each other in these differential rotation zones, and these collisions generated heat. Enormous amounts of heat. The temperatures in the inner accretion disk around Cygnus X-1 were estimated to reach millions of degrees Celsius. At such extreme temperatures, matter couldn't exist as solid, liquid, or even gas. It became plasma, a state where electrons are completely stripped from atoms, creating a soup of free electrons and atomic nuclei. This superheated plasma radiated energy across the electromagnetic spectrum, but the peak emission occurred in X-rays. This is how we detect black holes, not through the black holes themselves, which emit nothing, but through the brilliant glow of doomed matter spiraling into them. Black holes feeding actively on surrounding material, either from a companion star or from interstellar gas, become some of the brightest objects in the X-ray sky. Ironically, black holes can be among the most luminous objects in the universe, despite being dark themselves. The discovery of Cygnus X-1 opened the floodgates. Since that first identification, we've found thousands of black hole candidates. The evidence comes in various forms. Some, like Cygnus X-1, are detected through X-ray emission from accretion disks in binary systems. Others are found at the centers of galaxies, revealed by the motion of stars or gas clouds orbiting around invisible massive objects. We've identified stellar mass black holes in binary systems throughout our galaxy. We've found intermediate mass black holes in the centers of globular clusters, and we've discovered supermassive black holes lurking at the hearts of virtually every large galaxy we've examined closely enough. Some are relatively quiet, having long ago consumed nearby matter and now sitting dark and invisible, betraying their presence only through their gravitational effects on surrounding stars. Others are actively feeding, their accretion disks blazing with released energy, creating some of the most energetic phenomena in the universe. Quasars and active galactic nuclei. The variety is remarkable. Some black holes accrete matter steadily from normal companion stars. Others strip matter from red giant companions that have swollen to enormous sizes. Still others intercept stellar winds or capture interstellar gas. Each type of accretion creates somewhat different observational signatures, but the fundamental physics remains the same. As technology advanced, our ability to study black holes improved dramatically. We built more sophisticated X-ray telescopes like the Chandra X-ray Observatory and XMM Newton, capable of taking sharp images and detailed spectra of X-ray sources. We developed new techniques for detecting gravitational waves, ripples in space-time itself, allowing us to observe black hole mergers, events where two black holes spiral together and combine in collisions so violent they shake the very fabric of the universe. In 2015, the LIGO gravitational wave detectors made the first direct detection of gravitational waves, observing the merger of two black holes about 1.3 billion light-years away. The signal lasted only a fraction of a second, but in that brief time, the colliding black holes converted 3 solar masses of material into pure gravitational wave energy, making it temporarily the most luminous event in the universe, outshining all the stars in all the galaxies combined, though completely invisible to ordinary telescopes. And finally, most recently, we've even managed to take pictures of black holes. Well, sort of. In 2019, the Event Horizon Telescope collaboration revealed the first ever image of a black hole's shadow. This wasn't a simple photograph. It required combining data from 8 radio telescopes spread across the globe, from Hawaii to Chile to Antarctica, effectively creating an Earth-sized radio telescope with unprecedented angular resolution. The target was the supermassive black hole at the centre of the galaxy M87, about 55 million light-years away. Despite being one of the most massive black holes known, with a mass of 6.5 billion solar masses, its angular size in our sky is tiny, about 40 microarc seconds, roughly equivalent to seeing an orange on the moon from Earth. The image shows a dark circular region, the black hole's shadow, surrounded by a bright asymmetric ring of glowing material from the accretion disk. The asymmetry comes from relativistic effects. Material on one side of the disk is moving toward us at a significant fraction of light speed, making it appear brighter due to relativistic beaming, while material on the other side is moving away and appears dimmer. This achievement represented more than just a pretty picture, spectacular as it was. It provided direct visual confirmation that these objects exist, and matched the predictions of general relativity with remarkable precision. The size and shape of the shadow agreed almost perfectly with what Einstein's century-old equations predicted for a black hole of that mass. In 2022, the Event Horizon Telescope team revealed a second image, this time of Sagittarius A, the supermassive black hole at the centre of our own Milky Way galaxy. Though much closer to us than M87's black hole, Sagittarius A is also much smaller, making it similarly challenging to image. The result again confirmed our theoretical predictions. These images represent the culmination of decades of theoretical work and observational refinement. From purely mathematical speculation to direct visual confirmation, black holes have made the journey from impossible to undeniable. They're no longer theoretical curiosities, they're observed objects that we can study, measure, and even photograph. And yet, despite all we've learned, profound mysteries remain. What happens inside the event horizon? Does the singularity predicted by general relativity actually exist? Or does quantum mechanics intervene in ways we don't yet understand? Can information truly be destroyed in black holes, or must it somehow escape? These questions remain at the forefront of theoretical physics research. Accretion disks and X-ray emission. When material falls toward a black hole, it rarely plunges straight in. Most infalling matter has some angular momentum, some sideways motion relative to the black hole. As this material spirals inward, it forms a rotating disk called an accretion disk. Within this disk, incredible forces are at work. Matter orbiting closer to the black hole moves faster than material further out, creating shearing forces and friction. Particles collide violently with each other, and these collisions generate heat. Enormous amounts of heat. The temperatures in accretion disks can reach millions of degrees Celsius. At such extreme temperatures, matter exists as plasma, a state where electrons are stripped from atoms entirely. This superheated plasma emits radiation across the spectrum, but particularly in X-rays. This is how we detect black holes. Not through the holes themselves, which emit nothing, but through the brilliant glow of doomed matter spiraling into them. Black holes feeding actively on surrounding material become some of the brightest objects in the X-ray sky. Since that first discovery of Cygnus X-1, we've identified thousands of black hole candidates. We've found them at the centres of galaxies, orbiting other stars and scattered throughout interstellar space. Some are relatively quiet, having long ago consumed nearby matter and now sitting dark and invisible. Others are actively feeding. Their accretion disks blazing with released energy. We've even managed to take pictures of them. Well, sort of. In 2019, the Event Horizon Telescope collaboration revealed the first ever image of a black hole's shadow. Using a network of radio telescopes spread across the globe, effectively creating an Earth-sized telescope, they captured the shadow of the supermassive black hole at the centre of the galaxy M87. The image shows a dark circular region, the black hole's shadow, surrounded by a bright ring of glowing material from the accretion disk. This achievement represented more than just a pretty picture. It provided direct visual confirmation that these objects exist and match the predictions of general relativity. The shape and size of the shadow agreed precisely with what Einstein's century-old equations predicted. Can anything escape? For decades, the answer seemed obvious and absolute. No. By definition, nothing can escape from within a black hole's event horizon. That's what makes it a black hole. But in 1974, a young physicist named Stephen Hawking published a paper that challenged this certainty. He proposed that black holes might not be entirely black after all. Under certain conditions, they could emit radiation and gradually lose mass over time. Eventually, they might even evaporate completely in a spectacular explosion. This idea, now called Hawking radiation, sounds impossible at first. How could anything escape the inescapable? To understand Hawking's insight, we need to venture into the bizarre realm of quantum mechanics. Quantum fields and virtual particles. Let me ask you something that sounds simple. What is empty space? You might imagine a region of space with absolutely nothing in it. No atoms, no particles, no energy, no light, just nothing. Complete emptiness. But is it truly empty? Quantum physics tells us something remarkable. Even in the most perfect vacuum imaginable, with every particle removed and no energy passing through, something fundamental still exists. When a light wave travels through this empty space, it propagates as a wave. But waves need a medium to wave through. Ocean waves move through water. Sound waves move through air. What does light wave through? The answer is quantum fields. Quantum field theory proposes that all of reality is built from fields that permeate every point in space and time. There's an electron field, a photon field, a quark field, and so on for every type of particle in nature. These fields exist everywhere and everywhen throughout the entire universe. Where these fields are quiet, showing little activity, we perceive emptiness. But where a field resonates or oscillates with sufficient energy, that resonance manifests as a particle. An electron is simply an excitation in the electron field. A photon is a ripple in the electromagnetic field. This might sound like abstract philosophy, but it's actually how physicists understand the fundamental nature of matter and energy. You, me, everything we see, we're all patterns of vibration in quantum fields. Now here's where it gets weird. According to Heisenberg's uncertainty principle, one of the foundational principles of quantum mechanics, there are limits to what we can know about these fields. We cannot simultaneously know certain pairs of properties with perfect precision. For instance, we cannot know both the exact position and exact momentum of a particle. When we apply this principle to quantum fields, something extraordinary happens. The fields can't remain perfectly still. They must fluctuate randomly, even in empty space. These fluctuations occasionally become energetic enough to briefly create pairs of particles, a particle and its antiparticle twin. This might sound like science fiction, but we have experimental evidence. In 1948, Dutch physicist Hendrik Casimir predicted an unusual effect. If you place two uncharged metal plates extremely close together in a vacuum, they should experience a tiny attractive force pushing them together. Why? The space between the plates is so narrow that only certain wavelengths of virtual particle fluctuations can fit. Outside the plates, all wavelengths can exist. This creates a difference in quantum pressure. More virtual particles can pop into existence outside the plates than between them. This pressure difference should push the plates together. When the experiment was performed, the plates did indeed attract each other exactly as predicted. Something about empty space was pushing on the plates. These virtual particle pairs normally appear and disappear so quickly that they have no lasting effect. A particle-antiparticle pair pops into existence. The two particles almost immediately meet and annihilate each other, and they vanish back into the quantum foam from which they emerged. The universe's accounting books balance out, and we don't notice anything unusual. But what happens near a black hole? Hawking radiation. Explained. Stephen Hawking realized that black holes could disrupt this neat cancellation of virtual particles. Imagine the quantum fields fluctuating near a black hole's event horizon. Particle-antiparticle pairs constantly wink into existence and annihilate throughout space. But very close to the event horizon, something different can occur. If a virtual pair appears right at the boundary, one particle might fall past the event horizon while its partner remains outside. The particle that fell in can never come back out. It's trapped. But its partner, now unpaired, has nothing to annihilate with. It becomes a real particle, free to escape into space. From the outside universe's perspective, the black hole has emitted a particle, Hawking radiation. But energy cannot appear from nowhere. The radiation carries energy, and that energy must come from somewhere. It comes from the black hole itself. Each particle that escapes represents a tiny reduction in the black hole's mass energy. Over time, as the black hole continuously emits Hawking radiation, it gradually shrinks. Smaller black holes emit more radiation than larger ones, so as a black hole shrinks, the process accelerates. Eventually, in the final moments of the black hole's existence, it releases a tremendous burst of energy before vanishing entirely. This process is extraordinarily slow for large black holes. A solar mass black hole would take approximately 1067 years to evaporate completely, far, far longer than the current age of the universe. Supermassive black holes would take even longer, beyond any meaningful timescale. But for tiny black holes, if they exist, the story would be different. A black hole with the mass of a small mountain might evaporate in the lifetime of the universe, ending in a spectacular explosion as the last of its mass converts to energy. There's just one problem with Hawking radiation. We've never directly observed it. The radiation from astrophysical black holes is unimaginably faint, with wavelengths comparable to the size of the event horizon itself. For a stellar mass black hole, we're talking about wavelengths measured in kilometers. This radiation is also far colder than the cosmic microwave background radiation that fills all of space, making it essentially impossible to detect against the universe's background glow. However, recent experiments have provided indirect support for Hawking's mathematics, sonic black holes. Researchers at the Technion Israel Institute of Technology created what they called a sonic black hole, an analog system that mimics certain properties of a real black hole. Sound waves travel much slower than light, making them easier to work with experimentally. The researchers created a flowing medium, where the flow speed exceeded the speed of sound within that medium. Just as nothing can escape a region where space flows inward faster than light, sound waves cannot escape from a region where the medium flows faster than the local sound speed. According to Hawking's mathematics, such sonic black holes should emit an analogue of Hawking radiation, thermal phonons, or sound wave packets. After running the experiment nearly 100,000 times over several months, the researchers detected a signal matching Hawking's predictions. This doesn't prove that real black holes emit Hawking radiation. The physics is different in important ways, but it demonstrates that Hawking's mathematical framework applies to at least some physical systems, lending credence to the idea that it might apply to gravitational black holes as well. So if you fell into a black hole, could you ever escape? Not really. You'd be destroyed long before any prospect of evaporation. But in a sense, after waiting trillions upon trillions upon trillions of years, the mass and energy that once comprised your body might slowly leak back out into the universe as Hawking radiation. Not exactly a comforting escape plan. The footprint paradox. Let's conduct a thought experiment about causality, the relationship between cause and effect. When you walk on a beach and leave a footprint in the sand, the causal relationship is crystal clear. Your foot causes the footprint. The footprint doesn't cause your foot. This seems so obvious that stating it feels silly. But what if I told you that, when it comes to black holes and the curvature of space-time, this relationship might not be as straightforward as our intuition suggests? What if cause and effect could blur in ways that challenge everything we think we understand about how the universe works? To understand this possibility, we need to explore a different kind of relativity. Not Einstein's relativity, but Galilean relativity. Galilean and Einsteinian relativity. Galileo Galilei, centuries before Einstein, recognized something profound about motion. Imagine two identical rooms, one aboard a ship at sea, one on solid ground. Both are completely sealed with no windows. If the sea is perfectly calm and the ship moves at constant speed with no acceleration or turning, there is no experiment you could perform inside the sealed room to determine whether you're on the ship or on land. You're moving through space at vastly different speeds in the two scenarios, but you cannot tell the difference. Motion, Galileo realized, is relative. Without a reference point, the concepts of moving and stationary become meaningless. Einstein extended this idea dramatically. He proposed what's called the equivalence principle. Imagine again two sealed rooms. In one room, you're standing on Earth, experiencing normal gravity. In the other room, you're in deep space, far from any gravitating body, but the room is attached to a rocket accelerating upward at exactly 9.8 meters per second squared, the same acceleration as Earth's gravity. Einstein proposed that there is no experiment you could perform to distinguish these situations. The acceleration you feel from gravity and the acceleration from the rocket are fundamentally the same thing. This led Einstein to a revolutionary understanding of gravity. Gravity isn't a force that pulls on objects. It's the curvature of space-time. Objects in gravitational fields aren't being pulled. They're following the straightest possible paths through curved space-time, just as a ball rolling on a curved surface follows the contours of that surface. Massive objects create this curvature. The sun warps space-time around it, creating what we experience as its gravitational field. Earth follows a curved path through this warped space-time, which we perceive as an orbit. Physicist John Wheeler summarized it beautifully. Space-time tells matter how to move. Matter tells space-time how to curve. This seems to establish a clear causal relationship. Matter causes curvature, and curvature causes motion. Matter is the foot, curvature is the footprint. Or is it the non-locality of Hawking radiation? Here's where Hawking radiation introduces something deeply strange. Hawking radiation doesn't emerge from the black hole itself. It can't. Nothing can escape from inside the event horizon. Instead, it emerges from the curved space-time around the black hole. potentially quite far from the event horizon itself. For the largest supermassive black holes, with event horizons that could encompass multiple solar systems, Hawking radiation can appear billions of kilometers away from the event horizon. It emerges from the warped space-time geometry, from regions of space containing literally nothing but the curvature itself. As this radiation carries energy away, the curvature of space-time lessens. Less curved space-time means a less massive black hole. The black hole shrinks. Think about what's happening here. Energy leaves the curved space-time. The curvature decreases. The black hole's mass reduces. We're used to thinking black hole mass creates curvature. But here, it works in reverse. Reducing curvature reduces mass. It's as if the footprint got smaller, and as a result the foot shrank to match. This seems backwards, violating our intuitive sense of causality. How can the effect modify the cause? Einstein's field equations, the mathematical foundation of general relativity, state that the curvature of spacetime is proportional to the distribution of mass and energy. Proportional doesn't specify which is the cause and which is the effect. The equations work equally well whether mass creates curvature or curvature creates mass. Could it be that mass is actually a secondary phenomenon, a kind of shadow or projection, created by the curvature of spacetime itself? Imagine shining a light on your hand, creating a shadow on a wall. Normally we think of ourselves as the real thing, and the shadow as the projection. But what if we're the shadow? What if the fundamental reality is spacetime curvature, and mass is simply how that curvature manifests in our perception? We can't easily distinguish between these possibilities because we're stuck inside the system we're trying to analyze. From inside the universe, experiencing what we experience, both interpretations lead to the same observations. But if relativity has taught us anything, it's this. When two descriptions are observationally equivalent, we can't dismiss either one. Both must be considered potentially valid. This doesn't mean we're definitely living in a projection or simulation. The mathematics remains ambiguous. But it's a profound reminder that black holes, by pushing spacetime to its limits, force us to question our most basic assumptions about reality. Even if we are somehow projections of spacetime curvature, it doesn't really change anything practical. You still think, feel, and experience. Your subjective reality remains valid, but conceptually, it's rather unsettling to consider that when you ask, "Am I real?" the universe might answer, "That's a more complicated question than you think." Faster than light? Black holes seem to represent the ultimate cosmic prison. Nothing escapes. Nothing moves faster than light. These are absolute laws. Or are they? What if black holes could actually provide the key to faster than light travel? What if they could solve our energy crisis in ways we've barely imagined? And what if they accomplish both by fundamentally manipulating the fabric of spacetime itself? To understand these possibilities, we need to know more about what black holes actually are, beyond just their mass and event horizons. The three properties. Because nothing can escape from beyond the event horizon, we can't directly observe what's inside a black hole. This makes them remarkably simple objects to describe, at least from the outside. There are only three things we can measure about a black hole: mass, electric charge, and angular momentum, spin. Mass we've discussed extensively. It determines the strength of the gravitational field and the size of the event horizon. Electric charge works the same way around a black hole as around any charged object. A charged black hole will attract oppositely charged objects and repel similarly charged objects. By observing the motion of charged particles near a black hole, we can infer the black hole's charge. Most black holes in nature probably have very little net charge, as they form from electrically neutral stars and tend to attract equal amounts of positive and negative charges. But theoretically, charged black holes can exist. Finally, angular momentum spin. Almost everything in the universe rotates. Stars rotate, planets rotate, galaxies rotate. When a rotating star collapses to form a black hole, conservation of angular momentum ensures that the black hole rotates as well, often at tremendous speeds. We can detect this rotation through several methods, including its effects on orbiting matter and on the fabric of spacetime itself. These three properties, mass, charge, and spin, completely characterize a black hole from the outside. Two black holes with identical mass, charge, and spin are, as far as we can tell, absolutely identical in every way. This is sometimes called the no-hair theorem. Black holes have no other distinguishing features, like hair or other characteristics that vary between individuals. The ergosphere and frame. Dragging for rotating black holes' spin creates something extraordinary. The ergosphere. As a massive object spins, it drags space-time around with it like honey being stirred. This effect, called frame, dragging occurs around any rotating mass, including Earth. Sensitive experiments have measured frame dragging around our planet, confirming Einstein's prediction. Around a rotating black hole, frame dragging becomes extreme. The ergosphere is a region outside the event horizon where space-time is being dragged around so violently that it's impossible to remain stationary. Everything inside the ergosphere must rotate with the black hole, caught in the spinning whirlpool of spacetime itself. Near the event horizon, spacetime can be rotating faster than the speed of light. Wait, doesn't that violate Einstein's prohibition against faster-than-light motion? Not quite. Einstein's law states that nothing can move through space faster than light, but space-time itself can do whatever it wants. The expansion of the universe can and does carry distant galaxies away from us faster than light. Similarly, space-time near a spinning black hole can rotate faster than light. If you entered the ergosphere, you'd be swept along with rotating space-time carried around the black hole at tremendous speeds. From your local perspective, you wouldn't be moving faster than light through space. But relative to the distant universe, you could be moving at velocities that would appear to exceed light speed. This is the loophole black holes exploit, the Penrose process. In 1969, physicist Roger Penrose proposed a remarkable mechanism for extracting energy from a rotating black hole. Here's how it works. You send a spacecraft into the ergosphere. The spacecraft gets caught up in the rotation of space-time, accelerating to high speeds. At the right moment, the spacecraft splits in two, firing part of itself in such a direction that this piece falls into the black hole, while the remaining piece is flung out of the ergosphere. By carefully choosing the trajectory, you can arrange for the piece that escapes to carry away more energy than the original spacecraft had. You've extracted energy from the black hole's rotation. Penrose calculated that this process could theoretically extract up to 29% of a black hole's mass energy from its rotation. Remember Einstein's E, mc2. Even a small amount of mass represents enormous energy. To put this in perspective, nuclear fusion, the process that powers our sun and hydrogen bombs, converts only about 0.7% of mass into energy. The Penrose process is potentially 40 times more efficient than fusion. Of course, there are some practical challenges. You'd need to travel to a rotating black hole, ideally one without a scorching accretion disk that would vaporize your spacecraft. You'd need to survive the intense tidal forces near the ergosphere, and you'd need to execute the split and ejection maneuver with perfect precision. Not exactly feasible with current technology. But the theoretical possibility exists. More importantly, the Penrose process demonstrates something profound. Frame dragging is real, and it can create conditions that seem to violate our everyday intuitions about the speed of light limit. We haven't figured out how to use frame dragging for practical faster-than-light travel. Creating sufficient frame dragging would presumably require black hole levels of mass and rotation, which is rather beyond our capabilities. But knowing that such warping of space-time is possible, that frames of reference can move relative to each other faster than light, even though nothing locally exceeds light speed, opens conceptual pathways. It shows that the universe permits such things under the right conditions. Perhaps one day, we'll discover methods to warp space-time on smaller scales, creating conditions similar to the ergosphere without needing an actual black hole. That remains firmly in the realm of speculation, but it's speculation grounded in real physics, not fantasy. The difficulty of falling in, here's a surprising fact. Falling into a black hole is actually quite difficult. This seems counterintuitive. Black holes are the universe's most powerful gravitational sources, the ultimate cosmic vacuum cleaners. Shouldn't they be the easiest things to fall into? Albert Einstein himself believed it was essentially impossible to fall into a black hole, though he was thinking about it differently than we do today. The issue is conservation of angular momentum. Imagine dropping something directly toward a black hole, perfectly aimed at the center. In reality, this almost never happens. Nearly everything in space has some sideways motion relative to the black hole. This means the infalling material has angular momentum, a measure of its rotational motion. As material spirals inward toward the black hole, it moves to smaller and smaller orbital radii. Conservation of angular momentum is one of the most fundamental principles in physics. Angular momentum cannot simply disappear. It must be conserved or transferred to something else. What does this mean in practice? As the orbit shrinks, the orbital speed must increase to maintain the same angular momentum, just like a figure skater spinning faster when they pull their arms in. The skater's angular momentum stays constant, but as their moment of inertia decreases, arms pulled in means mass is closer to the rotation axis, their angular velocity must increase to compensate. The same principle applies to material falling toward a black hole, but with much more extreme consequences. Eventually, the material reaches speeds approaching the speed of light. It can't go faster. Nothing can exceed light speed. But according to the conservation of angular momentum to fall closer to the black hole, it would need to orbit even faster. It's reached an impasse. It can't orbit faster because of the light speed limit. It can't fall inward without orbiting faster. It's stuck. This is why accretion, disks form. Material can't easily fall straight in. Instead, it accumulates in a rotating disk outside the event horizon, slowly spiraling inward as various processes gradually remove angular momentum. Understanding accretion disks requires understanding several complex physical processes operating simultaneously. First, there's viscosity, friction between different parts of the disk. Material orbiting closer to the black hole moves faster than material further out, following Kepler's laws. This differential rotation creates shearing forces. Adjacent rings of orbiting matter are sliding past each other at different speeds, and this creates friction. In everyday life, friction converts kinetic energy into heat. The same happens in accretion disks, but on a far more dramatic scale. The friction between particles at different orbital speeds generates enormous amounts of heat. Temperatures in the inner regions of accretion disks can reach tens of millions of degrees Kelvin. At these temperatures, matter cannot exist as solid, liquid, or even gas. It becomes plasma, a state where atomic electrons are completely stripped away from their nuclei, creating a soup of free electrons and ions. This plasma glows brilliantly, emitting radiation across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. The peak emission frequency depends on temperature. For the hottest regions near the event horizon, where temperatures reach millions of degrees, the peak emission occurs in X-rays. This is why active black holes are such bright X-ray sources. We're seeing the thermal radiation from million-degree plasma in the inner accretion disk. But the viscosity that heats the disk also serves another crucial function. It transfers angular momentum outward. Through complex magnetohydrodynamic processes, the interaction of magnetic fields with the conducting plasma, angular momentum gets redistributed. Material in the inner disk transfers angular momentum to material in the outer disk through magnetic coupling and turbulent motions. This allows inner material to lose angular momentum and spiral inward toward the black hole, while outer material gains angular momentum and spirals outward. It's a self-sustaining process that gradually feeds the black hole while spreading the disk outward. The brightest accretion disks, called quasars, can be more luminous than entire galaxies. A single quasar can outshine 1 trillion stars, all from a region not much larger than our solar system. The quasar in the centre of the galaxy 3C273, one of the brightest known, has a luminosity of about 4 trillion times the Sun's luminosity. It's so bright it can be seen from 2.5 billion light-years away with amateur telescopes, despite being an object only a few light days across. To put this in perspective, if you replace the Sun with this quasar, it would be about 10 times brighter than the full moon appears from Earth, despite being 150 million kilometres away. It would be bright enough to read by at night, and it would be dangerous to look at even briefly during the day. This intense radiation carries away energy, and with it some mass. Between 10% and 40% of the original mass of the infalling material gets converted to radiation before the material crosses the event horizon. This makes accretion onto black holes extraordinarily efficient at converting mass to energy. Compare this to other energy generation processes we know. Chemical combustion, burning wood, coal, gasoline, converts about 1/10 billionth of mass to energy. Nuclear fission, current nuclear power plants, converts about 0.1% of mass to energy. Nuclear fusion, the Sun's energy source, converts about 0.7% of mass to energy. Accretion onto black holes converts 10–40% of mass to energy. Matter-antimatter annihilation converts 100% of mass to energy, but requires antimatter. Only matter-antimatter annihilation is more efficient than black hole accretion, and antimatter is extremely difficult to produce and store. Black hole accretion is the most efficient energy generation process that occurs naturally in the universe on large scales. Eventually, through these complex processes, material loses enough angular momentum to fall past the event horizon. But the details of exactly how this happens remain somewhat mysterious. The magnetohydrodynamics of accretion disks are extremely complex, involving turbulent flows, magnetic reconnection events, and plasma instabilities that we still don't fully understand. Some black holes with active accretion disks also produce relativistic jets, narrow beams of matter and energy shot out from near the poles at nearly the speed of light. These jets represent another mystery in black hole physics. Relativistic jets, cosmic particle accelerators. When I mentioned that falling into a black hole is difficult, that wasn't the whole story. Some material near black holes doesn't fall in at all. Instead, it gets ejected at nearly light speed in narrow beams that can extend for millions or even billions of light-years across space. These are called relativistic jets, and they're among the most energetic phenomena in the universe. Yet we still don't fully understand how they form. Here's what we know. Roughly 10% of active black holes with accretion disks produce jets. The jets emerge from near the black hole's rotation axis, essentially from the north and south poles if you imagine the accretion disk as the equator. They're highly collimated, meaning they stay narrow over vast distances, spreading out only slightly despite travelling across intergalactic space. The material in jets moves at speeds very close to the speed of light, typically 95–99% of light speed or higher. At these velocities, relativistic effects become crucial. Time dilates significantly, lengths contract in the direction of motion, and the mass energy of particles increases dramatically. When jets slam into the surrounding intergalactic medium, they create spectacular structures. The jets can carve out huge bubbles in the hot gas surrounding galaxies, creating radio-emitting lobes that dwarf the galaxies themselves. Some of these lobes are millions of light-years across. Current theories suggest jets form through the interaction of magnetic fields with the black hole's rotation. There are two main competing models, and both might be partially correct. The Blandford-Znaiec mechanism proposes that jets are powered by the black hole's rotation itself. Magnetic field lines threading through the event horizon of a rotating black hole can extract rotational energy, converting it into powerful outflows along the rotation axis. This process can tap into the black hole's spin energy, potentially extracting up to 29% of its mass energy. the same theoretical limit as the Penrose process. The Blandford-Payne mechanism proposes that jets are powered by the inner accretion disk. Magnetic fields anchored in the disk combined with the disk's rotation can launch material outward along the rotation axis through magnetocentrifugal acceleration. Essentially, the material gets flung outward along magnetic field lines like water off a spinning wheel. In reality, both mechanisms probably operate, with their relative importance depending on the specific configuration of each system. What's certain is that relativistic jets represent an enormous energy output. Some of the most powerful jets inject 1046 ergs per second into their environment, equivalent to the energy output of 100 billion suns. These jets can travel for millions of light years, carrying energy and momentum across intergalactic distances, influencing the evolution of entire galaxy clusters. Jets also create another observational phenomenon, relativistic beaming. When a jet points nearly toward us, the material moving at near light speed appears brighter and more energetic than it would if moving sideways or away from us. This is due to several relativistic effects combining. The Doppler shift boosts photon energies, time dilation increases the apparent rate of photon emission, and aberration focuses the radiation into a narrow cone pointed in the direction of motion. The result is that jets pointed toward us appear extraordinarily bright. These are called blazars. A jet pointed away from us might be almost invisible, while the exact same jet pointed toward us could outshine entire galaxies. This creates an observational selection effect. We're much more likely to discover black holes whose jets happen to point toward us, because they're so much brighter. Understanding the true population of jets requires carefully accounting for this bias. Jets also provide crucial information about black hole spin. The power of jets appears to correlate with black hole spin, consistent with the Blandford-Znaiec mechanism. By measuring jet power and luminosity, astronomers can estimate how rapidly black holes are rotating. This helps us understand black hole growth history. Black holes that grow primarily by steady accretion tend to spin rapidly, while those that grow through chaotic mergers tend to have lower spins. The information paradox. We've discussed Hawking radiation and how black holes might eventually evaporate. But this creates one of the deepest puzzles in theoretical physics, the black hole information paradox. The issue is subtle but profound. In quantum mechanics, information is never truly destroyed. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time, forward or backward. The evolution is deterministic and reversible, at least in principle. For example, if you burn a book, the information in the book isn't truly destroyed. It's scrambled and dispersed in the thermal radiation and smoke, but in principle, if you captured every photon and every molecule and knew their exact quantum states, you could reconstruct what the book said. The information is preserved in the radiation and ash, even if it's impractical to extract. But what happens when something falls into a black hole? According to classical general relativity, anything that crosses the event horizon is gone forever. It falls to the singularity and ceases to exist as a separate entity. From the outside universe's perspective, all information about what fell in seems to be lost permanently. Now add Hawking radiation. The black hole slowly evaporates, emitting thermal radiation, random photons with no apparent information content beyond their temperature. Eventually, the black hole disappears completely in a final burst of radiation. But where did the information go? What happened to the quantum information about everything that fell into the black hole over its lifetime? If the information is truly destroyed, this violates quantum mechanics' fundamental principle of information conservation. But if the information somehow escapes in the Hawking radiation, how does it get out? Hawking's calculation suggested the radiation is purely thermal, carrying no information about what fell in. Is completely random, like the radiation from any hot object. This is the information paradox, and it's troubled physicists since Hawking first proposed it in the 1970s. Stephen Hawking himself initially believed information was destroyed in black holes, suggesting that quantum mechanics needed modification. But this was deeply unsatisfying to most physicists. Quantum mechanics is one of our most successful and fundamental theories. Abandoning information conservation would shake physics to its core. In 1997, Hawking and Kip Thorne made a famous bet with John Preskill about whether information was destroyed in black holes. The stakes were relatively modest, an encyclopedia of the winner's choice, but the implications were profound. Over the following decades, evidence gradually accumulated suggesting information might be preserved after all. String theory calculations, the holographic principle, and advances in quantum gravity theory all pointed toward information being encoded on the black hole's event horizon and eventually escaping in subtle correlations in the Hawking radiation. In 2004, Hawking conceded the bet, acknowledging that information is probably preserved, though exactly how remains unclear. He gave Preskill a baseball encyclopedia. Thorne still hasn't conceded, believing the question isn't fully settled. Current leading theories suggest several possibilities. The holographic principle proposes that all information about what's inside a black hole is actually encoded on its event horizon, like a hologram encoding 3D information in a 2D surface. As the black hole evaporates, this information gradually gets released in subtle quantum correlations between different Hawking radiation particles. Correlations so subtle they'd be almost impossible to detect but theoretically present. Firewall theories propose that something dramatic happens at the event horizon itself, possibly a firewall of high-energy particles that would destroy anything trying to cross. This preserves information but creates its own problems, including violating the equivalence principle. Remnant theories suggest black holes don't evaporate completely, but leave behind tiny, stable remnants that somehow contain all the information about everything that fell in. But this seems to require these remnants to have essentially infinite internal states, which raises other puzzles. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests a deep connection between quantum entanglement and wormholes. In this view, entangled particles are connected by microscopic wormholes, and information might escape black holes through quantum entanglement with Hawking radiation particles. As of now, the information paradox remains unsolved. It sits at the intersection of quantum mechanics, general relativity, and thermodynamics, three of our most fundamental physics theories. Resolving it will likely require a complete theory of quantum gravity, which we don't yet have, but it highlights something important. Black holes aren't just interesting astronomical objects, they're laboratories for testing our most fundamental theories about reality. They push physics to its limits, forcing us to confront deep questions about the nature of information, time, space, and causality itself. Black hole thermodynamics. The information paradox connects to another surprising aspect of black holes. They have temperature and entropy, behaving in many ways like ordinary thermodynamic systems. This might seem strange. How can a black hole have temperature? Temperature relates to the random motion of particles, but black holes have no particles, just curved spacetime and a singularity. Yet the mathematics is compelling. Jacob Bekenstein first proposed in the 1970s that black holes should have entropy, a measure of disorder or the number of possible microscopic states. He argued that the entropy should be proportional to the surface area of the event horizon, not the volume. This was surprising. For ordinary objects, entropy usually relates to volume. More space means more possible configurations of molecules and thus more entropy. But Bekenstein argued that black hole entropy should scale with area. When Hawking calculated that black holes emit thermal radiation, it immediately implied they have temperature. Something emitting thermal radiation must have a temperature associated with that radiation. Hawking calculated the temperature of a black hole of mass T Kersky ASG C3, 8 pgm Kb. Where is the reduced Planck constant? C is light speed, G is the gravitational constant, and Kb is Boltzmann's constant. For a solar mass black hole, this works out to about 60 nanokelvins, 60 billionths of a degree above absolute zero. Extremely cold. For supermassive black holes, temperatures are even lower, sometimes only fractions of a nanokelvin. This is why we can't detect Hawking radiation in practice. The cosmic microwave background radiation left over from the Big Bang has a temperature of about 2.7 Kelvin, billions of times hotter than even stellar mass black holes. The Hawking radiation is completely swamped by the background radiation filling space. Interestingly, the temperature is inversely proportional to mass. Smaller black holes are hotter than larger ones. As a black hole evaporates and loses mass, it gets hotter, radiating faster, losing mass even more quickly. The process runs away in the final stages, ending in an explosive burst of radiation. The entropy formula is equally interesting. S net K to C3A. For G, where A is the area of the event horizon. For a solar mass black hole, the entropy is about 1054 kb, an enormous number. This is much larger than the entropy of the star that collapsed to form the black hole. Black holes have, by far, the largest entropy of any object of comparable size. This has profound implications. The second law of thermodynamics states that entropy always increases in closed systems. If black holes have enormous entropy, they represent the ultimate fate of matter in the universe, the maximum entropy state. The fact that entropy scales with area rather than volume hints at something deeper about the nature of spacetime itself. It suggests that the true degrees of freedom, the fundamental variables describing reality, might live on surfaces rather than in volumes. This idea evolved into the holographic principle, which proposes that our 3D reality might be a projection from information encoded on a 2D surface, similar to how a hologram creates a 3D image from a 2D film. String theory provided partial support for this picture. String theorists can count microscopic states of certain black holes and find results matching the Bekenstein-Hawking entropy formula. This provides our best evidence that black hole thermodynamics is real, not just a mathematical curiosity. Black holes thus obey laws analogous to thermodynamics. Zeroth law: the surface gravity is constant over the event horizon, analogous to temperature being constant in thermal equilibrium. First law: changes in black hole mass relate to changes in event horizon area, angular momentum and charge, analogous to the first law of thermodynamics relating energy, entropy and work. Second law: the event horizon area never decreases, analogous to entropy never decreasing. Third law: you cannot reduce a black hole's surface gravity to zero in finite time, analogous to being unable to reach absolute zero temperature. These mathematical parallels are too perfect to be coincidental. Black holes really do behave as thermodynamic objects, despite being purely gravitational phenomena. This suggests a deep connection between gravity, quantum mechanics, and thermodynamics that we're still working to fully understand. This seems counterintuitive. Black holes are the universe's most powerful gravitational sources, the ultimate cosmic vacuum cleaners. Shouldn't they be the easiest things to fall into? Albert Einstein himself believed it was essentially impossible to fall into a black hole, though he was thinking about it differently than we do today. The issue is conservation of angular momentum. Imagine dropping something directly toward a black hole, perfectly aimed at the center. In reality, this almost never happens. Nearly everything in space has some sideways motion relative to the black hole. This means the infalling material has angular momentum. As material spirals inward toward the black hole, it moves to smaller and smaller orbital radii. Conservation of angular momentum means that as the orbit shrinks, the orbital speed must increase, just like a figure skater spinning faster when they pull their arms in. Eventually, the material reaches a speed approaching the speed of light. It can't go faster. But to fall closer to the black hole, it would need to spin faster. It's stuck. This is why accretion disks form. Material can't easily fall straight in. Instead, it accumulates in a rotating disk outside the event horizon, slowly spiraling inward as friction and other processes remove angular momentum. Within the accretion disk, intense friction between particles at different orbital speeds generates enormous heat. Temperatures can reach tens of millions of degrees Kelvin. The material becomes plasma, stripped of electrons glowing brilliantly in X-rays and other high-energy radiation. The brightest accretion disks, called quasars, can outshine entire galaxies. A single quasar can be more luminous than 1 trillion suns, all from a region not much larger than our solar system. This intense radiation carries away energy, and with it, some mass, between 10% and 40% of the original mass of the infalling material. For comparison, nuclear fusion converts about 0.7% of mass to energy. Accretion onto black holes is extraordinarily efficient at converting mass to energy. Eventually, through complex processes we still don't fully understand, material loses enough angular momentum to fall past the event horizon. Some black holes with active accretion disks also produce relativistic jets, narrow beams of matter and energy shot out from near the poles at nearly the speed of light. These jets can extend for millions or even billions of light years, far beyond the galaxies that host the black holes. We've detected X-rays from jets originating from black holes over 12 billion light-years away. The exact mechanism creating these jets remains uncertain. Leading theories suggest that magnetic fields generated by the rotating plasma in the accretion disk or by the spinning black hole itself channel and accelerate material along the rotation axis, the one direction where the magnetic field structure permits escape. The size limits. How large can black holes become? Supermassive black holes at galactic centers can reach billions of solar masses. The largest known black hole, TON 618, has a mass of approximately 66 billion suns. Its event horizon is enormous enough to contain multiple solar systems. Interestingly, some of the most massive black holes we observe are also among the most distant. Distance in astronomy translates to looking back in time. Light from TON 618 has travelled 10.8 billion years to reach us, meaning we see it as it was when the universe was only about 3 billion years old. This creates a puzzle. Our own Milky Way's central black hole, Sagittarius A, has existed for over 13 billion years, but masses only about 4 million solar masses. TON 618, despite being much younger, is roughly 15,000 times more massive. Why would young black holes be more massive than older ones? Shouldn't older black holes have had more time to accumulate mass? Several factors contribute to this apparent contradiction. First, detection bias plays a role. We can only observe the most distant black holes when they're active quasars, blazing with the light of infalling matter. Inactive black holes at those distances would be invisible to us. This creates a bias toward observing especially massive black holes at great distances. They're the only ones bright enough to see. Second, the early universe was different. In the first few billion years after the Big Bang, matter was more densely packed. Gas clouds were larger and more abundant. Galaxies collided more frequently. All these factors meant more fuel available for black hole growth. As the universe expands and ages, matter becomes more spread out. Gas clouds deplete as stars form. The rate of galaxy mergers decreases. Less fuel means slower black hole growth. Third, black hole growth isn't unlimited. Radiation from the accretion disk creates outward pressure that can actually prevent more material from falling in. There's a theoretical limit called the Eddington limit, beyond which radiation pressure should halt further accretion. Finally, many large black holes reside in elliptical galaxies that have already consumed most of their available gas. With no fuel remaining, these black holes sit dormant, no longer actively feeding. As the universe continues to age and spread out, active quasars become increasingly rare. In our local cosmic neighbourhood, within 500 million light-years, we observe no quasars at all. They're all distant, all ancient, all showing us conditions from the younger universe. So while it appears that the largest black holes are the youngest, this might be an observational illusion. Older supermassive black holes might exist but remain dark and invisible, having long ago consumed their available fuel. White holes and wormholes. We've spent considerable time exploring black holes, but they're not the only exotic solutions to Einstein's equations. The mathematics of general relativity also permits white holes and wormholes, structures that, while theoretically possible, we've never observed. Think back to a simple mathematical shape, a cone. If I ask you to imagine a cone, you probably picture something pointing upward, like a traffic cone, or downward, like an ice cream cone. These are real-world cones. But the mathematical definition of a cone actually describes two cones joined at their points, one pointing up, one pointing down. Real-world cones are just portions of this complete mathematical structure. Black holes are similar. The black holes we observe in nature are formed from collapsing stars, representing one part of a more complete mathematical solution. The full solution includes a white hole, essentially a time-reversed black hole. Instead of a region from which nothing can escape, a white hole would be a region from which things can only exit, never enter. Matter and energy would emerge from a white hole but could never fall in. To visualize this, physicists use Penrose diagrams, which represent infinite spacetime in a compact form. In a Penrose diagram for an eternal idealized black hole, one that's always existed rather than forming from a collapsing star, we see four distinct regions. Region 1 is our familiar universe. Region 2 is the black hole interior, separated from Region 1 by the event horizon. Nothing can escape from Region 2 to Region 1. Region 3 is the white hole, with a different kind of horizon. Things can exit from Region 3 to Region 1, but nothing can enter Region 3 from Region 1. Region 4 is a parallel universe, another exterior region separated from our universe by both the black and white holes. This structure exists in the mathematics, but does it exist in reality? For black holes formed from collapsing stars, probably not. The formation process doesn't create the white hole or parallel universe portions of the full mathematical solution. But could white holes exist independently? Could they have formed in the early universe? Could they represent the final stage of black hole evaporation? One intriguing hypothesis suggests that when a black hole completely evaporates via Hawking radiation, it might transition into a white hole in its final moments. The mathematics of loop quantum gravity, one approach to reconciling quantum mechanics with gravity, suggests this possibility. In this scenario, a black hole would shrink via Hawking radiation until reaching the Planck mass, about 20 micrograms. At this scale, quantum gravitational effects dominate, and our current theories break down. Loop quantum gravity suggests the black hole might quantum tunnel into a white hole state, subsequently releasing its remaining mass energy. This could potentially resolve the black hole information paradox, the question of what happens to information that falls into a black hole. If that information eventually emerges from a white hole, information would be preserved rather than destroyed. These ideas remain highly speculative. We have no observational evidence for white holes, but they're not unscientific speculation. They're logical extensions of established physics into unexplored territory. Wormholes. Wormholes represent another exotic possibility permitted by general relativity. For rotating or charged black holes, the mathematical description becomes more complex than for simple, non-rotating black holes. The singularity isn't an inevitable destination. Instead, these black holes have inner structures that could theoretically permit passage through to other regions of spacetime. In a rotating black hole, the singularity takes the form of a ring rather than a point. If you could somehow survive crossing the event horizon and navigate the interior carefully, you might pass through this ring and emerge into a different region of spacetime, possibly a different universe. The pathway connecting these regions is called a wormhole. The mathematics allows for it, but practically several obstacles make traversing such a wormhole nearly impossible. First, the interior of a black hole is turbulent and deadly. Tidal forces would tear you apart. High-energy radiation would incinerate anything attempting the journey. Second, even if you could survive the interior, the wormhole itself appears to be unstable. The slightest disturbance, like a human-sized object trying to pass through, might cause it to collapse before you could complete the journey. Third, from the perspective of the external universe, infinite time would pass as you fell through the black hole. By the time you emerged into the other region, your original universe would have aged past the end of time itself. So while wormholes might exist in the mathematical structure of space-time, using them for practical travel seems beyond impossible. Still, they remind us that space-time can be far stranger than we imagine. The universe permits these exotic geometries, these connections between distant regions of space and time. That they exist at all, even just mathematically, expands our understanding of what's possible. The big picture. We've covered enormous ground in this exploration of black holes, journeying from the depths of massive stars to the edges of theoretical physics. Let's take a moment to synthesize what we've learned and consider what questions remain. We've seen how black holes form from the violent deaths of massive stars. When the largest stars in the universe exhaust their nuclear fuel, they collapse catastrophically under their own gravity. The result is a gravitational field so intense that not even light can escape from within a certain boundary, the event horizon. This boundary isn't a physical surface, but a mathematical demarcation in space-time itself, the point beyond which return becomes impossible, not because of any force or barrier, but because of the geometry of space-time itself. We've understood that what we see as a black sphere in images isn't the black hole itself, but the event horizon, marking where space-time curvature becomes so extreme that all paths lead inward. The actual black hole, possibly an infinitely dense singularity, remains, forever hidden behind this veil. We've explored how black holes warp not just space but time as well, creating situations where two observers can experience radically different realities, yet both be correct within relativity's framework. An observer falling into a black hole experiences a finite time before destruction, while an outside observer never quite sees the crossing happen, witnessing instead an eternal freeze frame slowly fading to invisibility. We've discovered how we detect these invisible objects through the brilliant glow of their accretion disks. Matter spiraling toward a black hole, heated to millions of degrees by friction and compression, emits intense X-rays and other radiation. Ironically, black holes feeding on surrounding material can become among the brightest objects in the universe, despite being fundamentally dark themselves. We've delved deep into quantum mechanics and Hawking radiation, learning that the seemingly empty vacuum isn't truly empty but seethes, with quantum fluctuations. Near a black hole's event horizon, these fluctuations might manifest as real particles escaping into space, causing black holes to slowly evaporate over incomprehensibly long timescales, a process so slow that for stellar mass black holes it would take 10 carbon-67 years, far longer than the current age of the universe, yet fast enough that tiny black holes, if they exist, might explode spectacularly in the far future. We've questioned causality itself, wondering whether mass creates space-time curvature or whether curvature creates mass. Hawking radiation, emerging from curved space-time far from the event horizon, and thereby reducing the black hole's mass, hints at a universe where cause and effect might be more intertwined than our intuition suggests. Perhaps mass is not the fundamental reality, but rather a manifestation, a projection of space-time curvature itself. We've explored how rotating black holes drag space-time around with them, creating ergospheres where remaining stationary becomes impossible. We've seen how the Penrose process might theoretically extract energy from this rotation, energy conversion more efficient than nuclear fusion by a factor of 40. And we've understood how frame dragging demonstrates that while nothing can move through space faster than light, space-time itself faces no such limitation, opening conceptual pathways toward faster-than-light travel, if we could ever learn to manipulate spacetime curvature on smaller scales. We've examined the surprising difficulty of falling into a black hole, understanding why accretion disks form and why some material gets ejected in relativistic jets rather than absorbed. We've seen how these jets, extending millions or billions of light years across space, carry energy comparable to the output of billions of galaxies, shaping the evolution of galaxy clusters and the large-scale structure of the universe. We've grappled with the information paradox, one of the deepest puzzles in theoretical physics. Does information get destroyed when it crosses the event horizon, violating quantum mechanics? Or does it somehow escape in Hawking radiation? And if so, how? This question sits at the intersection of our three most fundamental theories: quantum mechanics, general relativity, and thermodynamics, and resolving it will likely require breakthroughs in quantum gravity. We've discovered that black holes have temperature and entropy, behaving surprisingly like ordinary thermodynamic objects, despite being purely gravitational phenomena. Their entropy scales with the area of the event horizon rather than volume, hinting at the holographic principle, the idea that reality might be fundamentally lower dimensional than it appears, with our 3D experience being a projection of information encoded on 2D surfaces. We've ventured into the realm of white holes and wormholes, mathematical solutions to Einstein's equations that might or might not exist in our universe. White holes, the time reverse of black holes, from which matter can only exit, never enter. Wormholes, hypothetical tunnels connecting distant regions of space-time or even different universes entirely. While these remain speculative, they're not scientifically invalid. They're solutions to established equations, even if nature may not realize them in practice. Through all of this, one theme emerges clearly. Black holes push physics to its absolute limits. They exist at the boundary of our understanding, where general relativity meets quantum mechanics, where time and space lose their familiar meanings, where causality itself becomes questionable. The future of black hole research. Where do we go from here? What questions remain, and how might we answer them? Several frontiers of black hole research are particularly exciting. Gravitational wave astronomy has opened an entirely new window on the universe. Since LIGO's first detection of merging black holes in 2015, we've observed dozens of black hole collisions. Each observation tests general relativity and strong field regimes and teaches us about black hole populations, how many exist, how they're distributed across masses, how fast they spin, how they form and evolve. Future gravitational wave detectors will be even more sensitive. The Laser Interferometer, Space Antenna, LISA, planned for the 2030s, will detect much longer wavelength gravitational waves from orbit, observing supermassive black hole mergers throughout the universe. The Einstein Telescope and Cosmic Explorer, next-generation ground-based detectors, will see neutron star and black hole mergers from the earliest cosmic epochs. These observations will help answer crucial questions. How did supermassive black holes grow so rapidly in the early universe? What fraction of stars end their lives as black holes? How common are intermediate mass black holes? How do black hole spins evolve? Event Horizon telescope observations will continue improving. The 2019 image of M87's black hole and the 2022 image of Sagittarius A were just the beginning. Future observations with more telescopes and longer baseline observations will produce sharper images and even movies showing matter orbiting and accreting onto black holes in real time. These observations will test general relativity even more precisely. Does the shadow size and shape exactly match predictions? Are there any deviations that might hint at modifications to general relativity or quantum gravitational effects? Quantum gravity remains the holy grail. Merging quantum mechanics with general relativity, understanding physics at the Planck scale, where both become important, remains one of the greatest challenges in theoretical physics. Black holes, where quantum effects meet extreme gravity, provide crucial testing grounds for any proposed quantum gravity theory. String theory, loop quantum gravity, causal set theory, and other approaches all make different predictions about quantum black holes. Observations might eventually distinguish between these theories, guiding us toward a complete description of reality. The information paradox continues to drive theoretical research. Recent developments like the island formula and calculations of entanglement entropy have provided new insights, suggesting information really is preserved. But the exact mechanism remains unclear, and different physicists favour different resolutions. Progress here will likely illuminate fundamental aspects of space-time, entanglement, and the nature of information itself. Black hole interiors remain completely mysterious. What actually exists inside? The event horizon? Is there really a singularity, or does quantum gravity resolve it into something finite? Could black hole interiors connect to other regions of space-time, or even other universes? Do the exotic features predicted by rotating and charged black hole solutions, inner horizons, ring singularities, possible pathways to other universes, actually exist? Or are they mathematical artifacts that realistic collapse erases? We may never know the answers to these questions through direct observation. You can't send a probe inside and have it report back. But theoretical work, guided by what we can observe at and near event horizons, gradually illuminates possibilities. Primordial black holes remain a possibility. If black holes formed in the early universe from density fluctuations during cosmic inflation, they could have a wide range of masses, including very small black holes that might be evaporating through Hawking radiation now. Some scientists speculate that primordial black holes might account for some or all of dark matter, the mysterious substance comprising 85% of the universe's matter, but interacting only gravitationally. Searching for primordial black holes, either directly through gravitational effects or indirectly through the radiation from evaporating examples, remains an active research area. Their discovery would revolutionize our understanding of both the very early universe and particle physics. Black holes as cosmic laboratories will continue to be invaluable. The extreme conditions near black holes, intense gravity, strong magnetic fields, relativistic velocities, extreme temperatures, create natural laboratories for testing physics under conditions we can never reproduce on Earth. Observations of matter and energy near black holes probe regimes of pressure, density, and energy that inform our understanding of fundamental physics. Why black holes matter? Beyond the pure science, beyond the mathematics and observations, why should anyone care about black holes? First, they're part of our cosmic heritage. The heavy elements in our bodies, the iron in our blood, the calcium in our bones, the gold in our jewellery, were forged in stellar interiors and blasted into space by supernovae, many of which left black holes behind. We are, quite literally, made of stardust, including stardust from stars that became black holes. Understanding black holes helps us understand where we came from. Second, black holes drive galaxy evolution. Supermassive black holes at galactic centres aren't just passengers, they're active participants in how galaxies grow and change. Jets and winds from accreting black holes can heat the gas in galaxies, preventing star formation. This feedback process appears crucial for understanding why galaxies have the properties they do. Without black holes, the universe would look very different, and we might not be here to observe it. Third, black holes push us to question our assumptions about reality itself. They force us to confront deep questions. What is space-time fundamentally? Is information fundamental to reality? Could we be projections from a lower dimensional surface? What happens at the boundary of quantum mechanics and gravity? These aren't just idle philosophical musings, they're concrete questions that black holes force upon us. Fourth, black holes inspire wonder. In an age where much seems explained and understood, black holes remain profoundly mysterious. They remind us that the universe is stranger and more wonderful than everyday experience suggests. They show us that reality operates according to principles that defy intuition and common sense, yet are mathematically precise and observationally confirmed. For children and adults alike, black holes capture imagination. They represent the frontier of human knowledge, the edge of what we understand. They show that we don't have all the answers, that mysteries remain, that there's still so much to discover. Finally, the quest to understand black holes drives technological and theoretical progress. Developing gravitational wave detectors required advances in laser technology, materials science, vibration isolation, and data analysis. Event Horizon Telescope observations pushed the limits of radio astronomy, timekeeping, and computational technique. Theoretical work on black holes has spawned new mathematical tools, new approaches to quantum field theory, and new ways of thinking about information and computation. Often, the practical benefits of fundamental research appear only decades later in unexpected ways. GPS satellites depend on understanding relativity, something that seemed like pure abstract theory when Einstein developed it. Quantum mechanics, once viewed as bizarre and impractical, now underlies computers, lasers, MRI machines, and countless modern technologies. Who knows what future technologies might emerge from truly understanding quantum gravity, information theory, or the nature of space-time itself? A final reflection. We began this journey by calling black holes mind-bending, and I hope you now understand why. They're not just objects in space, they're challenges to everything we think we know about reality. They show us that time is not absolute but can slow down or speed up depending on gravity and motion. They demonstrate that space can be so severely curved that straight lines lead in circles, that escape becomes impossible not through force, but through geometry. They reveal that the vacuum isn't empty but seethes with quantum activity, that particles can appear from nothing and return to nothing, that the boundary between something and nothing is far blurrier than common sense suggests. They hint that causality might not flow in one simple direction, that effects might modify causes, that mass might be secondary to curvature rather than primary. They suggest that reality might be holographic, that our 3D experience might be a projection, that information might be more fundamental than matter and energy. They force us to confront the limits of knowledge itself. What happens inside an event horizon where no information can escape? Can we even meaningfully ask what exists there if it's fundamentally unobservable? Yet despite all this strangeness, despite all these challenges to intuition, black holes are real. They exist, we observe them, we can measure their properties, we can test our theories against their behavior. They're not fantasy or speculation. They're concrete objects we can study and understand, at least partially. This is the beauty of physics at its finest. Reality is under no obligation to match our intuitions, to make sense according to everyday experience, to behave the way we'd prefer. Yet it follows precise mathematical laws we can discover through observation and reason. We can understand things wildly different from everyday experience by following the mathematics wherever it leads and checking our predictions against observation. Black holes exemplify this perfectly. They're so strange that Einstein himself initially doubted they could exist. Yet here we are, having photographed them, observed them merging through gravitational waves, measured their masses and spins, confirmed their properties match theoretical predictions to extraordinary precision. We stand today at a remarkable point in history. A century ago, black holes were purely theoretical speculation. 50 years ago, we just identified the first candidate. 20 years ago, we'd never observed gravitational waves from black hole mergers. 5 years ago, we'd never imaged a black hole's shadow. Progress continues to accelerate. New observatories come online. New theoretical insights emerge. The next few decades promise even more remarkable discoveries. Perhaps we'll observe primordial black holes and learn about the first fraction of a second after the Big Bang. Perhaps we'll resolve the information paradox and understand how quantum mechanics and gravity unify. Perhaps we'll image black holes well enough to test general relativity in unprecedented detail and detect any quantum corrections to the classical theory. Or perhaps, and this is what makes science exciting, we'll discover something completely unexpected, something that forces us to revise our entire understanding once again. That's what black holes do. They keep surprising us. They keep challenging us. They keep showing us that no matter how much we learn, mysteries remain. So the next time you look up at the night sky, remember, scattered among those stars, invisible yet undeniably present, are holes in the fabric of space-time itself. Regions where our reality breaks down, where physics becomes strange beyond imagining, where questions about the nature of existence itself remain unanswered. They're out there, silently warping the cosmos around them, waiting for us to understand them more fully. And the journey to that understanding, the journey we've taken together today, reveals a universe far more strange, far more wonderful, and far more mysterious than we could ever have imagined. Thank you for joining me on this exploration of black holes, these cosmic enigmas that push the boundaries of human knowledge and imagination. If you found this journey as fascinating as I hope you did, please consider liking this video and subscribing to Late Space for more deep dives into the mysteries of the cosmos. The universe is full of wonders, and we've only begun to scratch the surface. Until next time, keep looking up, keep asking questions, and never stop wondering about the strange and beautiful reality we inhabit. The cosmos has more secrets to reveal, and black holes will undoubtedly play a central role in uncovering them. Keep exploring, keep questioning. And remember, in the grand cosmic story, black holes aren't just curiosities. They're key characters in the narrative of how our universe works, how it evolves, and perhaps even in understanding what reality fundamentally is. The darkness at the heart of black holes might just illuminate the deepest truths about existence itself.